Hey guys, so welcome back. Today we're going to look at resonance and we're going to look at it in AC circuits. So when you have elements of resistor, inductor and capacitor all connected in series, current expression is given by this expression that I have right here. So your IRMS is equal to VRMS by square root of resistance square plus XL minus XC square. So XL is and XC are impedance offered by your inductor and capacitor. So this expression is nothing but Ohm's law. So in Ohm's law we have V equals IR. So I equals V by R. So instead of R, this R is replaced by Z, which is impedance in AC circuits, and that Z is the entire value under the square root. So that is the expression for Z, and this expression is nothing but simple Ohm's law. Now let's plot this. Okay, so I'm gonna plot my Z first. So my impedance starts off at a high value and it changes with frequency and it hits low at a certain point and it raises back again. So what is shown in green is my impedance. Alright, now I'm gonna plot in yellow the current. So when the impedance is high, current is low. So current starts off low and it reaches maximum when the impedance is lowest, and once again as impedance climbs high, the current drops back down. So this is current. Okay, so now this point, this one particular frequency where current is maximum is called resonant frequency, and resonance is said to occur. And the expression for this simplifies to, if you look at this expression right here, XL minus XC. So when XL and XC are equal, it simplifies to just V RMS by R. So that is the condition for resonance, that is XL equals XC. Now how do we find this resonant frequency? So this resonant frequency, if we simplify this expression, we know XL is omega L. I'm going to write it as omega naught because that is how the frequency, angular frequency at resonance is denoted, and XC is 1 by omega naught C. So that is the expression for impedance. And if you just simplify for omega, you would get 1 by square root of LC. So I'm just gonna erase this a little bit. That is the simple formula to find at what frequency resonance occurs. So if you know what is the value of L, and if you know what is the value of your capacitor, you can easily plug those values in and to this formula and say, okay, I have my frequency here, so that is when resonance will occur. And what is the significance of resonance is you have the maximum amount of current flowing in that circuit. So you can pretty much design all your circuits to have rating components that have rating for this current right here. Okay, so let's look at some formulas before we go ahead and solve our problems. Like I said, here we have these elements connected in series. So this is a case of series resonance. Now in series and parallel resonance, there are some similarities. So that is when resonance occurs, that your impedance is equal to your resistance. So this condition is same because your impedance offered by the inductor cancels out with the impedance offered by the capacitor. So basically all the opposition you have in the circuit is from the resistor. So this case is same whether it's a series resonance or a parallel resonance. And so this is XL and this is XC, and that is the same. So when to find the resonant frequency, you would just use this expression or the much more simplified expression that we saw right here, that is omega naught is 1 over square root of your inductance times capacitance. Alright, now let's see what is these two values called Q and BW. BW is nothing but bandwidth. Okay, I've drawn this much more clearly here. So here I have my current peaking at certain value. So if I get I max by root 2, and this is gonna cut the curve at certain frequency. So this frequency range is known as bandwidth. So what's the importance of bandwidth? So bandwidth basically tells you if your curve is flatter or it's much more sharper. So let's say I have higher bandwidth, so my current resonance curve is going to look like this. It's going to be much more flatter. So if I have a lower bandwidth, that means this gap is really small, so my curve is much more sharper. So that is the significance of bandwidth. And lastly, we are back here and we look at this term called Q. So the Q factor in a parallel resonance circuit is called current multiplication factor. We're going to look at it in one of our problems. So right now, all you got to remember is this expression. And don't worry, because you don't have to memorize these. You just have to know what is the Q value. And it's always going to be in your reference book if you're taking the FE exam. So don't worry about that at all. Now let's go ahead and solve some problems on these. Okay, so my first problem says I need to find the resonant frequency for this circuit. So it's a series resonance circuit, and I need to find the bandwidth. So I have 10 microfarad capacitor, 100 ohm resistor, and 20 millihenry inductor. So it's quite simply a substitution problem. We know that resonance occurs when XL equals XC, or simply omega naught L equals 1 by omega naught C, or omega naught equals 1 over square root of LC. So this is the simplified expression. So now we gotta find omega naught. So omega naught is 1 over, my L is 20 millihenry, so that's 20 into 10 power minus 3, and my capacitor value is 10 microfarad into 10 power minus 6, and extend this. So my angular frequency is going to be, if on solving this, I would get 2236 radians per second. Now sometimes you can get confused, but saying that they have asked for resonant frequency and we're just finding omega naught. The simple thing is this omega naught is just equal to 2 pi f naught. So you can keep the answer in angular frequency, or if you want your resonant frequency in hertz, you can just go ahead and divide this value by 2 pi. That's how you get it in hertz. Now let's go ahead and find the bandwidth. So the bandwidth for this circuit would be, well, let's see what was the expression for bandwidth for series resonance. So for series resonance, our bandwidth right here is omega naught by Q, and let's get started with that. It's omega naught by Q. So to find the bandwidth, first we need to find what is Q. So then Q value is, if you remember, omega naught L by R. So I'm going to go ahead and write this. So bandwidth is equal to omega naught divided by omega naught L by R. So omega naught and omega naught will get cancelled, so that will leave me with my final answer. Bandwidth is R by L. And that is, my resistance in this circuit is 100 ohms and my inductance is 20 millihenry. So my bandwidth is going to be 5,000 radians per second. So what that means is, in our resonance curve, the curve goes somewhat like this. So this is my Imax, and Imax by root 2 is here, and the gap between this point and this point, that is 5,000 radians per second. Okay, so it's quite simple to understand, and it was a pretty easy problem to solve. So in your FE exam, if all these formulas are going to be in your reference book, and all you need to do is substitute them. Now let's go to the next problem. The next problem says, calculate maximum current of an RLC circuit shown. Okay, so I got my RLC circuit here, 10 microfarad, 10 ohms, 10 millihenry, 120 volt supply, and I need to find the maximum current. So let me go ahead and write the expression once again for maximum current. So I max is V RMS divided by R. So why is it just R? Because your maximum current is going to occur at resonance. So if you looked at the curve, this is your Imax, and this is going to occur at resonance when XL minus XC equals 0. That's a fancy way of saying XL equals XC. So when your XL equals XC, that's when you have your maximum current, and that is going to cause resonance to occur. So that would simplify the entire expression of your IRMS equals V RMS by, this is impedance, so that is under the square root of R square XL minus XC the whole square. So this whole term becomes 0. So I'm just left with IRMS, or in this case it will be maximum, is V RMS, and square root gets cancelled, it's just R. So here my supply is 120 volts, and let's see what was my resistance value. It was just 10 ohms, and that would give me a maximum current of 12 amperes. Sorry. So in this curve, I'm having this, and this value here is 12 amperes. Quite simple, right? So if you're an engineer and you have these elements in your circuit, and you want to know, okay, I'm going to get a maximum current in this circuit, what is that maximum current going to be? You use this very simple formula, VRMS by R. You don't have to worry about XL or XC because they're going to cancel out each other at some point, and that point is exactly when you'll have your maximum current. Alright? Okay, so let's move on to our next problem. So our next problem says, calculate the current magnification factor of RL. So let's move on to our next problem. our next problem says calculate the current magnification factor of RLC circuit. So I have here a parallel RLC circuit. It's got 3 branches and I need to find the current magnification factor. So what is current magnification factor? This is nothing but Q. And that is because in a parallel resonance circuit, the current in either your inductor or your capacitor branches is Q times the main current. So if you have main current I, the current in, let's say, the capacitor branch is going to be equal to Q times the main current. Just putting it in the modulus so that we can just take the absolute value of it. So this acts kind of like a magnification or a scalar value. So that's why it's called current magnification factor when it comes to parallel circuits. So now let's go ahead and find Q for a parallel circuit. So for a parallel circuit, the value of Q was omega naught RC or R by omega naught L. So I'm going to use omega naught RC. So Q is going to be omega naught RC. That's nothing but, so okay, here I've hit a roadblock. What is my omega naught? So once again, if you remember, I'm gonna write it here. Omega naught is 1 over root LC. Okay, so I'm just gonna write it directly here. So it's gonna be RC by root LC. So this is my value, the expression for finding Q. Now let me go ahead and substitute the values. So Q was RC by LC. So my R was right here, 10 ohms into capacitor, 100 microfarad. Under the square root, my inductor value was 10 millihenry. Sorry, it wasn't 10. My inductor was 20 millihenry. So this is going to be and capacitor once again 100 microfarad. Okay, so if we go ahead, do all the math in this one, we are gonna get a final answer of 0.707. Now remember, Q does not have any units, so the quality factor does not have any units. So we found this as 0.707. So what that means is in this circuit you have some main current. So the main current is related to inductor current or capacitor current by Q times main current. So this Q value we found here is 0.707 times main current.